this approximation for binomial works out really well, there are a couple of things that we have to consider because we're dealing with representing discrete data on a continuous scale. So we've got to make some allowances for that. So let's just consider for a second that we use the density curve in general for continuous data, which is measurable. Oops, curve for continuous data, which is measurable, which includes our decimal values. Well, let's call this measurable. So decimals, I wanted to jot that down too. But so, and on our curve, we think about it on the density curve, that's all represented down here. Here are our x's. For each x, we can find a corresponding z. Again, this is continuous data. So maybe, for example, we're talking about heights. That would be something measurable, and those are represented along a scale. Maybe the mean is here at 70 inches. So again, we've got this continuous scale, but there are no gaps in here. We don't have a gap between 70 and 71, and so on. So the question is, how will we represent discrete data, individual values on this scale? So let's just consider maybe we're talking about here, our x is discrete, and we're talking about number of survey responses. And maybe we're at 60, but then the next one is we either got 60, 61, 62, and so on. But there are gaps between the data. There's not 60.5 survey responses. Someone either gave a response or they didn't. So remember, with our discrete, this is our gaps between those values. We have to account for those gaps in the data values, and to do so, we use something called the continuity correction. All right, and what we're going to do is we're just going to basically add or subtract 0.5 to our x values in order to close that gap. So let's see what I mean. So let's even just say that we're talking about our survey responses. Remember, those would be our x's, and then for each one, we'd have the probability of getting some number of responses. So maybe it's 0, 1, 2, all the way down to 100. Well, for this many, we certainly would not want to have to use a probability distribution. So instead, we're going to use, or in other words, we don't use binomial. So instead, we want to use the normal approximation. So let's assume for this example, we're just kind of making up an example here. We're going to assume that the mean for this is going to be 3. All right, I guess it's just because that we have a decimal value in this case. So the mean might be at 60.3, but the x's can really only be whole numbers. But how are we going to fix this is that we are going to do something, and I mark it as x sub c. It's x corrected. So this is x corrected. And this is where, if we want to find, for example, we're going to represent, if we wanted to talk about 72 responses, we're going to represent this as an interval. So we'll say the interval represents 72 with what? Well, 72, maybe it's right here. So here's our, okay, and again, we're talking about just value, but it doesn't make sense on our normal continuous curve. So what we're going to do is we're going to take the value just above it, we're going to say, well, if this is x, then I can call x corrected. One of them would be 72 plus 0.5. In other words, we've got x corrected maybe sub 2 is 72.5. And we can have one just below it, x corrected maybe sub 1, is equal to 72 minus 0.5, or in other words, x corrected 1 is equal to 71.5. So remember that when we're using the normal curve, we're talking about area between. Find then the probability of getting 2 by calculating area. However, a line, if we just drew a line right up at 72, a line doesn't have any area to it. So that's why we've either got to add or subtract, or in this case, both. We've got to add 0.5 and subtract 5. So if we want to find the probability of getting exactly 72 of, say, 100 responses, then we've got to find the area between those. So we use the interval. And let's, next page, we're going to take a look at a bunch of common examples just to clarify this. So let's go ahead, wrap this one up, and then we'll go on and look a couple of examples. And you might even want to flip over to the next page and see if you can maybe figure out what some of those might look like.